So good afternoon in Japan and in Taiwan. So guten Tag. It's my great pleasure to have Dr. Steffen Plunder from Kyoto University. And today he's going to share us a very interesting and for us maybe exotic topic about modeling on the directionality of cell migration. We understand this is a very fancy and very important topic for science. So, and this modeling is related to the so-called non-smooth dynamic system. I think most of us are familiar with smooth dynamic system, and we are really curious about how you treat with the non-smooth dynamic system. So that's welcome him.
Thank you, everyone. Thank you for the nice introduction. I have not given an online talk in a long time, but every interruption or questions are most welcome. And yes. If you have ideas or comments, I'm always very interested. So I'm at the moment a postdoctoral researcher at Kyoto University in the Institute of Advanced Study of Human Biology. So all my neighbors are biologists and there are only a few mathematicians around. So I'm also always happy to talk about mathematics. So today I want to talk like 50% mathematics or a bit more. And then in the second half, I show the biology. And to show you a little bit what I do in most of my work, usually I try to talk with the biologists to understand how I can model some biological tissue or some cell migration. So today I will present the model on EMT. I will explain later what that is. That is some tissue which we were modeling. Out of this work, I also started working on cell migration and particular type of cell migration. And with some collaborator from France, with Michel, we also implemented a bacteria model. And what all these three different models have in common is that they are locations where there are a lot of cells packed. So it's high density and high pressure. And this is where the non-smooth to give a little bit of teasers, I was thinking like, okay, what does non-smooth dynamics have to do in a seminar on nonlinear dynamics? So if we are considering particle systems, like we have positions x1 to xn for n number of cells or disks or spheres, then usually we have a force f of x, which is the smooth dynamics, and maybe we want them to not overlap, and then we have a repulsion force, volume exclusion force. So if we have hard constraints,
yeah, you just stop sharing screen. Don't worry. Yeah.
Yeah. Okay. I try to reconnect. Okay.
Yeah.
So we can look at the sets Sij, which is very important in this talk. The set Sij, which tells us for two particles, do they overlap or not? And this is the complement of a convex set. But now if we are taking the union of all of these sets, then we get the sets of S where none of the particles are overlapping within a radius R. And this set is not convex at all. And this is a bit of the challenge of today's talk. And so what we could do with smooth dynamics is that we could penalize over entering the forbidden set of overlap. We just replace the volume exclusion with the gradient of the distance function. And the further we go into the set, the more we want to go back. And gamma is here penalty parameter. And if we compute that gradient, it's very similar in principle to this kind of interaction sums, which we have in particles models where we take the gradient of some repulsion potential. So this would be the smooth dynamics approach. But what we see, we have a parameter here, and we get these functions we need to define. What we could do is we could go non-smooth. We say, let gamma go to infinity. And if we then imagine a distance function, it will grow and grow, and it will get steeper and steeper until we get an indicator function. And non-smooth dynamics can be seen as the limit system we get if we replace such a smooth potential with this non-smooth limit here. The indicator function is 0 or infinity. And later I will explain this in much more detail and slower, but what we could then attempt is that we solve this differential inclusion where we say the velocity minus the forces has to be in a certain set. And the set is, in one interpretation, it's the subdifferential, which is a very complicated tool in a way. And the geometric interpretation of this is going to be the normal cone. And what is nice about this is that in this kind of model, we don't have any parameter anymore. So gamma is gone. And as I want to show in this talk today, simulating those non-smooth dynamics can be faster and easier in a way than simulating the smooth dynamics under terms and conditions. Yeah. So a little bit of a warning. Non-smooth dynamics is sometimes really tricky. So for example, for smooth dynamics, there's kinetic theory where we can derive PDEs from cell migration models. But if we have hard spheres, then there are phenomena which indicate that we might never the cells are blocking each other from going in from this bridge-like structure. But if I move one of the cells just a tiny little bit, then it would break the blockade and the cells could move in. So that shows that like just a movement, like a change on a set of measure 0 always, almost, could completely change the behavior. And there's recent work by Bertrand Moret about this kind of issue. I'm not going to talk about this today, but just as a warning, like non-smooth dynamics can be very difficult. Okay, so now, because the topic is maybe a little bit exotic, I thought I will first give an introduction to non-smooth dynamics, like a mathematics lecture, and it's not my own research. This is like established research. So my work for my PhD, where we found we analyzed the numerical method. And interestingly, this method was invented by NVIDIA. And we basically we didn't invent the method, but we analyzed it mathematically. And this method then we used for this modeling of epithelial-to-mesenchymal transition. So that's the outline of the talk. And in some sense, the key result is that we could show this numerical method works using the theory of non-smooth dynamics. And this method somehow was much, much faster than alternative methods for simulating such a tissue with crowded environment. Yeah, so that's the plan. Let's start with the mathematics. Here I have a small simulation which shows a very simple setup where I want to demonstrate the difference between the penalty method and this position-based dynamics method. So at the moment, I use the position-based dynamics to simulate these cells, and it works fairly well. Now, if I change to the penalty method and simulate the same setting, what we will see is that cells start to overlap. And then in a good way. And what we observe if we penalty strength, sorry, the penalty strength parameter. If we increase the penalty strength parameter, what we will see is that the system becomes stiff and unstable. Because, you know, from numerical analysis, simulating a system with a large gradient is hard, and we need good solvers for that. But the interesting thing is that the PDB method can simulate the same setup with hard constraints with the same delta t, and there's no oscillations and no instability. And this is kind of the numerical takeaway. And I want to explain how this works. So let's start with the mathematical foundations. Please interrupt me if I should go faster or if this is less interesting. Yeah. Because the audience is very qualified here. You're all more experienced researchers than me.
Really, don't worry, yeah.
So we all know differential equations. And so these are equations without any constraints. And then differential algebraic equations might be written in this form where we have a constraints function g, and we want it to be 0. But in addition, we need to modify the dynamics now so that we stay on the manifold. And this means we need, for example, Lagrange multiplier. And this is for equality constraints. So I will draw down the image here a little bit. So this DRE setting is we have forces in any direction, but with our Lagrange multiplier, we will correct our velocity onto the tangent space so that we stay within our manifold M. And if we look at this decomposition, then we see, okay, the forces is decomposed into the tangent space and the orthogonal part of the tangent space, which is the normal space. And this will become more important in a second. So how can we do inequality constraints? Inequality constraints, we can use dynamic complementarity. As we do for equality constraints, we again have a Lagrange multiplier. And this time we want a function g to be non-negative. But if we just say g non-negative, then we cannot compute the Lagrange multiplier uniquely. So we need more conditions. And this is like the KKT conditions from optimization. So we have the condition that the Lagrange multiplier must be non-negative. And then we have this complementarity condition, which says if we are on the boundary of the constraint, like either g of x is 0, then lambda can be anything. But if g of x is positive, so we are on the boundary, we are in the inside of the set, then lambda needs to be 0. So lambda can only be active when we are on the boundary of our feasible set. So there's a lot of geometry hidden in this dynamic complementary systems. And this is usually dynamic complementarity systems are good for numerics, but very bad for analysis or mathematics. Because it's not so easy to write existence theorems or anything or to know that it's good. So this is where differential inclusions came historically into play. So differential inclusions allows us to reformulate the same equations as follows. We say the velocity minus the forces has to be in the negative normal cone. So that is the same image as what we had for the differential algebraic equations, that the velocity minus the forces are in the negative normal cone. But now our set is not a manifold, but it's like a manifold with boundaries. So the normal cone is really a cone, like the admissible velocity are all the velocities here in the blue set. And the normal cone is orthogonal to the tangent cone. And interestingly, there was a question.
So why is your cone C convex? Or you assume? So you assume C is convex, or?
Yeah, I will. Normally you would want to assume this, but I will drop the
Okay.
Find this with C convex, and then everything is equivalent. Yeah. For C not convex, it becomes more complicated.
Okay.
Yeah. Yeah. So, and if C is convex, it's relatively easy to show that these two systems are equivalent, just using the definition of a normal cone and tangent cone. Okay. So now, in this introduction, to give really a feeling for how it is to work with non-smooth dynamical systems, I want to talk about what are the geometric requirements for working with normal cones, and very shortly state existence and uniqueness. So I will not go into much theory, but just show one example that you know how to work with such systems. So basically it means that the map between X and the map towards the normal cone, this map needs to be sufficiently nice, and it needs to be monotone or hypomonotone. And let's do a little bit of why are convex sets not enough? Like I mentioned in the introductions, if we have cell migration, then usually we want to consider something like the set of non-overlapping cells, and this set is not convex. You can easily see that, like for example, the cell X4, it is not overlapping with X1 at the moment, but if you jump over X1, it's also not overlapping, but in between there's a state where they would overlap, so it's not convex. And the notion which is now established to deal with that issue is uniform prox regularity. When I was working on my PhD, I started with a programming modeling background, and someone gave me actually the model I had to work on, and that model was formulated in a way where it was not clear if there are solutions at all. So it took me like one and a half years to find the right theory. But once you find it, it's super obvious that everybody knows already. What are prox regular sets and proximal normal cones? To recall, so for a convex set, we can define the normal cone by saying all velocities, I have an image, all directions, so that the scalar product, here in this image, you can imagine the direction n, and then you look at the direction from x to y, so y minus x. And if the scalar product is always negative, then it's a normal vector. That's the definition for a convex set. But here I've drawn a non-convex set, and you can see how this definition fails. Like here, the scalar product between y minus x and n is positive, but this is actually a normal vector in this sense, locally. So prox regularity the idea came by saying we want something like a convex set, but only in a small environment. So the easiest definition is, okay, first I define the projection, which we all know, the orthogonal projection. I write the set onto which we project as a subscript. And then we can say a set S is eta prox regular if for every x, which is in S plus epsilon distance, eta for my set S, for these points, the projection is unique. And one intuition one can form from that is that your set cannot have very sharp inside angles. That's the only thing. But the set I've drawn here is totally fine. Like all curvatures which are non-convex, they have to be bounded by eta essentially, by a sphere of radius eta. So prox regularity for a convex set, we know that projection onto convex set is always unique. So this is a definition stronger than convexity. Yeah, and now in this setting, there are two definitions for the normal cone, which we have to use. If I'm starting at a point x, I go in the direction of the normal vector with distance eta, and then if I project back onto my set, I land at the same point. For something which is a normal vector going away from your set, you need this property. And because of the uniform prox regularity, we also know that this projection is unique. So we can really write equality here. And this is very closely related to the convex condition. If you look here in the convex condition, we have the scalar product that is negative or non-positive. And here we could equivalently write this also like the scalar product is less or equal to quadratic penalty term. This is like a very, like this shows how this is related to convexity. Historically, this was called weak convexity. Okay, so now we are almost done with the hardest math or the definitions. Now I want to show how this is useful for dealing with these kind of differential equation problems. So there's a very easy computation one can do in a convex case. If I take 2 points from my set and 2 normal vectors, then these scalar products are now negative, and then I can subtract these two from each other, and then I can get the scalar product of the normal vector from my one normal cone minus the normal vector from the other normal cone. Here, like written as it is here, this is non-negative, non-positive, sorry, non-positive. This is called a monotone map. So the convex normal cone, X mapping onto its normal cone, this is called a monotone map because of this property. And now it's not hard to see that for Prox regular set, we get a similar property. With the same calculation, we use the normal cone condition with the quadratic penalty. And then we subtract the two from each other, and then we get this equation here. And this is called hypomonotone. And if you're working in this domain and with analysis, then this will be your biggest friend. That's why I wanted to show this equation, even though it's a little bit technical.
Why do we have this prefix, hypo? Why hypo? That's curious.
Oh.
Where's the name from?
Actually, I think I don't know.
Okay, fine. I will check it out.
I had a feeling it's something like hyperbolic, but I'm not sure. I'm not exactly sure.
Thank you. Yes, thank you.
And here x and y is swapped by accident. Yeah, it should be x minus y. Yeah, okay. So normal cones have this property. And then already then we have the basic property we need for existence and solutions of our models and equations. So just to read it out, so if we have such a Prox regular set and we want to stay inside the set, and we write a differential inclusion which implements that, then we only need that the forces are Lipschitz continuous in addition, and then we get a unique solution, and the solution is absolutely continuous, which means that for almost every time point t, the time derivative exists. But on a set of measure 0, it might not exist. But in particular, the solutions are continuous. So these are functions one can work with, so to say. And then there was further work, for example, by Juliet Venel, who extended it to Banach spaces, and then also Bernard Rogliato has written a recent review where he gives a nice overview over this field. So these are the references I would recommend. Yeah. So since we are mathematicians and doing analysis, I don't want to give the full proof because nobody can follow a proof online. But the idea is it is possible to show in the setup that the velocities have a bounded norm. And once we have that these have a bounded norm, one can use something like Acela Ascoli and a weird form of continuity. And I will skip that today because it's a bit technical to write down. But it follows ideas from the Peano theorem for differential equations. And for uniqueness, we use the hypomonotonicity. And this is very simple, so I want to show just the uniqueness proof. So if we consider that there are two solutions of our system, then we, like x of y dot minus f of y of t. If we have two solutions of our system, then we could compute a time derivative between the square norm of the two solutions. And then if you compute the time derivative of a square norm, then you get the velocities minus the difference in the scalar product. And using this equation from step 1, we know that the velocity we can replace with your differential inclusion. So we know there's a normal vector v of x and v of y, and minus the forces v of x, f of x and f of y. So this is just inserting our differential inclusion. And now the first term here, this is exactly what hypermonotonicity was about. Hypermonotonicity bounds this guy. And because on the right side, with Lipschitz continuity, we also get a bound. So combining those two, we can apply Cronval or something they like, and then we get that the distance between the solutions depends on the initial condition plus a term which we can bound. So that's how the analysis in this domain looks like. Okay. So to finish the small introduction to non-smooth dynamics, basically, so if we have a feasible set which is uniformly Prox regular, then there is a well-established existence and uniqueness theorem and somehow theorems like stability estimates. And the important example is that applies in particular for non-overlap between particles. So that means we have a mathematical framework for which we can build and construct a model. So before I go to the application, I want to show the numerical method which we use there. So for the So for the numerical method, quality constraints uses basically one method, mostly, which is called Moreau's sweeping process. It means you use an Euler step or something more fancy, and you project onto your set S. That's very simple. Go, like make some error in your constraints and then project back and be happy. And projecting back is hard. Like this is a hard problem for non-convex sets. And most of the numerical methods are about how can we find a good projection method. And because this is hard, we usually use implicit solvers for that. We use some optimization methods to compute this projection. So to give two references, like good books for dealing with contact mechanics are from Peter Wiggers or from Vincent Akari. Non-smooth modeling and simulation. Also a good point, like because I'm talking with people from Taiwan, like differential equations are also very classical or important to simulate electronic circuits. Because in electronic circuits, there are also situations where we have inequality constraints due to, I think, Kirchhoff's law. Not completely sure. Yeah. So there's a lot of theory also in that direction, but I was only interested in the contact, so I'm not an expert on the other part. So now I want to show you this method, which is very cool, which people. So I was playing computer games and I was wondering why are my simulations so slow and the computer games so fast. And then I found this method which is used in computer games, which is called position-based dynamics. And I have here some video of what this method, for example, can do. It is very popular in computer graphics for fluid dynamics, where we replace the fluid in a smoothened particle method. So, and here all of the particles of that fluid have a hard non-overlap constraint. And this turns out to be somehow good for computer graphics to make such nice simulations. And what is interesting is that this method can also deal with very complicated large deformations. Some solid mechanics simulation with non-overlap, so self non-overlap, which is even more complicated, and merging and everything. And these computer scientists, they can pull it off. So there has been a lot of research on these kind of numerical methods in computer graphics. Vertex block descent is also a very nice, very recent method for solid mechanics. And this method is also used in, like recently, this year, there was a big conference in Taiwan where Omniverse was presented. And NVIDIA Warp is another simulation framework by NVIDIA, and both of them use position-based dynamics. From computer science, computer graphics are not the best because they are optimized to be really good looking. So position-based dynamics is actually mostly implied for second-order dynamics. In physical systems, that's what we usually have. And interestingly, here the method does not converge. It's not physically accurate. The method is looking good, but it's not real, so to say. And what I found is that for first-order dynamics, it is actually accurate. So in biological systems, we often have overdamped motion. So first-order Newton equations. And this means that this method, which usually is only heuristic, in our setting in biology, it is a really capable simulation method we can use for real science.
So Stefan, I have a question here.
Yeah.
I mean, any ODE can be made first order. You have a Newton equation, you can have a two equation of first order. What do you mean by first order dynamics?
Yeah, that's a very good question. So that is possible if you have enough smoothness. So you can take the time derivative if you have enough smoothness. And this is why you can transform it. But here in these kind of systems, your x is maybe, in this setup, x is not even continuous. X would be, or x is just continuous, and then the velocity is.
I see your point. Oh, that's very delicate. That's very delicate. Yeah, I see.
Yeah.
Okay.
And this is a real problem. Yeah. But it is a good question because otherwise, yeah, we could use it.
But then I don't understand why in this non-smooth setting, second order is better for PBD, because of the damping or?
The second order is not so good. So for the physics simulation,
the second order is good because you say PBD can be applied to second order, right? This is my definition of good.
So it can be, people use it and it looks very pretty, but it's not a convergent numerical method because it converges to the wrong limit. But the wrong limit looks good and it converges very fast to that. And the reason is for the second order PDB method for Newton equation, they use some extra trick, which I'm not showing at the moment. There is some extra trick which makes the method very stable, but throws away all physics.
Okay, so your contribution is to make the PBD method to be applied into first order dynamics.
Yeah.
And this is new.
Maybe, I hope so.
Okay. Interesting. Thank you.
Thanks for the question. Yeah, so generalizing PDB for first order is actually very simple. So that is not the main contribution in a sense. And the method is really nice to implement. So if we have some first order differential inclusion and our set S is the intersection of simple sets Sj. So if it is easy to satisfy set Fj, then we could come up with the idea that we take our take the output and project onto the next set S2 and so on. And For non-overlap, for example, if I have two particles and they overlap, the projection is very simple because we just have to move those two particles away from each other by the right hand mouse. So no computational effort. So the idea of first order position-based dynamics is just do this projection and then proceed to the next time step. So basically we replace the projection by this iterated projection. Now, classical convergence proof would somehow now say, oh, that's a problem, because this iterated projection, that's something we know. There's a method, projected Gauss-Seidel method. If we repeat these iterated projections over and over and over again, like here in this image, we would see that we would converge to the projection, to the real projection onto the set S. But for position-based dynamics, we stop after one step. But the nice part is that doing these projections costs a lot of time. How does this compare with making delta t h 10 times smaller? Because when delta t h is 10 times smaller, my violation, the new inequality violation, will become also 10 times smaller. So this job is easier. So the people from NVIDIA, they compared that, and there's this nice video here, which shows us how it looks like. So left is the mathematically accurate method with large delta t, and it's unstable. Right is the sloppy projection, just k is equal to 1, but it's very stable because we make delta t 10 times smaller. And this is the magic of this method. Yeah, so, and here, after the end of my period, converges, and you can also do convergent plots and then show that this method is better in computational cost compared to other methods. So the blue line here is position-based dynamics, and it's below alternative methods we could use. So it has a smaller error at the same computational cost. And I also published a Julia package where you can simulate differential inclusions in Julia. And you just can define the, for example, non-overlap constraints, and then solve an ODE problem with additional constraints. Okay. So here, the real convergence theorem is a bit long and very technical. So I think maybe I will skip that part for the moment and go to the biology applications. But if someone has questions later, I can go back here. So blub, blub, blub. Yeah. So the conclusion of this part 2 is, okay, position-based dynamics, somehow a very powerful method, which we maybe want to use for modeling in biology. And here, this is a simulation I did using a GPU, also using position-based dynamics. Okay, now let's come to the most challenging part of biology. So now I will swap from mathematics to biology. So I have to explain a little bit of biology terms. And please interrupt me if I should go a little bit slower. So the project I was working on was about epithelial-to-mesenchymal transitions. So here's an image of epithelial-to-mesenchymal transition. So epithelium is something like skin cells. So our skin is an epithelium, but also inside of our body there's epithelium, like skin-like cells inside our body. The cells are connected to their neighbors, and the cells are connected to the basal membrane where they have a good stability. So it's a very structured tissue. But what can happen is that some of these cells might get a signal which tells them, please change your cell type. We need you to do another function in the body maybe. So if a cell starts to transform into another cell type, into a mesenchymal cell, it can detach from its neighbor and it can start to migrate. And so it will change a lot of biophysical properties and then go typically into the basal direction. So examples for epithelial to mesenchymal transitions are into normal embryo development. So in the beginning, all cells are epithelial cells. And very early, the primitive streaks forms and our spine develops. And you might not know it, but many of our brain cells are coming from our spine initially because they perform EMT and then they migrate into the head location. So it's very good that EMT exists. However, EMT is also famous because it is part of the hallways of cancer. So one of the 7 hallways is EMT, and what happens there is that skin cells or epithelial cells, they become tumor-like. They start to migrate using EMT and migrate into our body. And then they can maybe hit a blood vessel. And when they hit a blood vessel, then they might enter our blood system, which is very bad. And they can even do the reverse mechanism. They can transition back into epithelial cells somewhere else in our body. So in the cancer setting, we don't want that the cells go in the basal direction. We would like them to go into the apical, into the other direction where they are just dying. So in this project, we were asking the question, like, how can we determine the directionality of EMT? And for this, we worked together with a biologist, Eric Thevenau from Toulouse. And he has a model for EMT, which is the chick embryo. So here you see a chick embryo schematic from the head anterior to the tail posterior. And when we are slicing somewhere, then we see this tube, which is the neural tube. And between the 13th and the, within the first 2 days, the neural tube is growing a lot because all the cells are proliferating. And these cells here are epithelial cells, and they have this particular form that they have a nucleus in one region and a very slim body everywhere else. It's like a tennis ball in a sock. And in this kind of tissue, in this tissue, we can trigger EMT. But before we could model EMT, we had to establish a model for the healthy tissue. So one key property of this particular tissue is that the cells are always dividing on the upper side, on the apical side. At fluorescence, these are the cells performing cell division, mitosis. And you see that the position of cell division is always very much on the apical side, very well controlled. This is called interkinetic nuclear migration. So our first goal was to model this kind of tissue. And you can also see that there are a lot of cells. So this was published by a PhD student before me, Maria Ferreira, with Eric Thevenau. And they established a model which looks like this. And I will now roughly explain this model. So we see that in this model, the cells are moving up, then they are dividing on the apical side, and then they're moving down. So this model is an agent-based model, and it has 2 components, so to say. The first component is the mechanical model, how we model an And then the second part is what happens within the cell cycle. And I already explained what we will do is that we will contract one of the springs of the cell so that it moves up. So the basally located cytoskeleton will expand, and then the cells move up, and then they divide on the apical side. I will explain this model in a second in more detail. But with this starting point, we have a good model for epithelial tissue, which is very simple. Like there are no assumptions which are very critical, so to say. We don't introduce a bias towards apical or basal movement. Yeah. And to connect this now to the mathematical part, here in this system, we wanted that the cells are a little bit flexible, but they should have a certain volume exclusion in another area so that they cannot infinitely compress. And the way how this was modeled was a combination of a hard sphere and a soft sphere. And I used this also in other cell migration models. It's a very easy way to model such cells. So here the smaller sphere is the hard sphere and the larger sphere is the soft sphere where we have repulsion with a smooth potential. Spring on the bottom, which is the cytoskeleton. Like inside the cell, there are microtubes and they can expand. And on top, we would have the cell-cell interaction, which we model here very simple with just springs between my neighbor for apical junctions. So very minimal assumption model. On the basal, it's even simpler. We just say there's the spring attached to the x-axis, and there's a maximum distance between my left and right neighbor. So in terms of differential inclusion, that means that I have the hard sphere inequality constraint, and I have the basal distance inequality constraint, and also there were some other inequality constraints which we added for experiments. And the nice thing is all of these feasible state for an individual constraint. And to use this as a modeling tool, that's basically the ingredient. What you need is you need inequalities constraints which are simple, and then it's very easy to implement. Yeah, and if we do that, then we get these dynamics which I shown earlier. So now that's nice. Let's make it more complicated. Now we want to introduce EMT. Now we want to take some of the cells and transform them, let them transform in their phenotype. And this was published last year in Nature Communications on two different systems. Like one was on the chicken, which is what I'm showing today. And then there was a second application of the same mathematical model on mouse gastrulation. Yeah, so how do we add EMT to this model? The first part is that we have to introduce the biological phenotype changes. So a mesenchymal cell is not attaching to the apical layer anymore. So what we do is we just cut the apical springs and allow these cells to remove maybe happen, which is the same can happen with the basal domain. The cells can detach from the basal side, and then the cells can lose their straightness. That's not so an important factor, but the cells somehow want to be on a straight line, and which determines their polarity, and we can disable that factor. And finally, we could have a cell which starts to migrate actively in one direction. So it could be that the cells are using protrusive activities after they detach from the basal membrane. Biologically, it was not so clear when this is going to happen, if this happens at the beginning or at the end of EMT. So now we have these 4 events, A, B, S, and P. And we can say, when does it happen? Does it happen at all? Yes or no? That's what the biologist was interested in. And that's also a case for mathematicians. This is now not very interesting, actually, this question, because it's just like trying out a lot of combinations. So before I show you the combinations we tried, here a little bit of the textbook. So if you are reading a textbook about EMT, then there's a nice sequence of things. So apical side, that's logical. Then maybe you change your polarity a little bit, and then you detach finally from the basal side, and then you start with the migration. So this is the textbook model. And if you're implementing this, this would be A, loose apical adhesion, S, loose polarity, B, loose detachment from basal membrane. And when we do that, the simulation looks quite nice. It actually happens that the cell is very close to the basal membrane. But the same simulation with another initial condition, it happens like in 10% of the cases that the cell is actually going out on the apical side. So why can that happen in this logical sequence? If a cell is on the apical side, and when it loses the detachment to the basal layer, it will just fall off the apical. So that was a bit of a surprise to us when we were starting the modeling. So I made a simulation and I sent it to Eric, and I was like, oh, Eric, I'm really sorry. I made a mistake. This should give basal extrusion, but it's falling off on the apical side. How can I fix it? And Eric was like, oh no, you should not fix this. Maybe this is interesting. Maybe this is the real biology. And in this case, I have a very good collaborator, and I was very happy that he realized that moment. So what we then started doing is that we ran Monte Carlo simulations. We said, oh, let's try all different parameters and try to characterize when do we fall off the basal side, when do we fall off the apical side. And here one trick which I learned from the biologist as well is that we mathematicians would represent this data very differently, but because he could represent it in a biology style, I think it was more successful in the biology journal. And what we found is, the first thing is that protrusions are actually really, really important to determine the direction. That's not a surprise, because protrusions make the cell act, which is different than what biologists assumed. But instead, the position when the event starts is very important. So instead of timing, we should think about timing and position, basically, as the key factors. And here I have written that we ran, so to get these kind of correlation analysis, and to connect this to the numerical method I told you about earlier. So when I came, there was a Fortran-MATLAB combination which somehow had the effect that running one simulation was 30 seconds per simulation. Then I changed to Julia code and cleaned up a little. And run more simulations, we would have waited 13 days for this analysis. Now with this position-based dynamics method, the runtime went down to 0.04 seconds. So that meant we could do these Monte Carlo simulations like every day, try out a little bit different instead of waiting 2 weeks. So that's the happy story here. So to show you the two results which we found, I told you earlier that the cells are moving to the apical side when they're dividing, internuclear migration. So what we found in the simulations is that internuclear migration has a big factor on the direction of extrusion. It makes sense. If your cells are more often going to the apical side, they might have higher chances to fall off on the apical side. And Eric could do experiments where he did the following. He looked in the chicken embryo at different levels on the posterior anterior axis. And in the chicken, it is like this, that EMT is earlier in the head region and happens later in the tail region. So because of that, if we are having an embryo and we make this picture, so we cannot take a video from the embryo, we only have one snapshot. And if we have one snapshot, by looking at different locations, we can look at different settings. The first one here is where EMT is already happening, very advanced. And we can see that there are some cells which do cell division far away from the apical layer. And these are the EMT performing cells. So we see that non-apical mitosis happens a lot in the EMT part. But the surprise was that already before EMT is actually starting, the cells already stop doing internuclear migration. So this was the biology result here, that we found INM is regulated already at the beginning of EMT and not just after EMT. And the second result, here I will not go too much into the details. When we looked at what all combinations can, so here what we did is in biology, people really like to look at heterogeneity. Normally, cells perform different scenarios. Every cell is a little bit different from their neighbor. So how does it change the behavior if all the cells are doing the same versus all the cells are performing different phenotype changes? And what we did here is we simulated a lot of heterogeneous groups of cells, and then we modulated how much ENM internuclear migration is happening and how many of the cells perform protrusions. So here it means 50 of the cells perform protrusions and 50 of the other cells do not perform protrusions in one simulation. And what we found here, there are two predictors for basal extrusion. It's less internuclear migration and more protrusive activities. So we have these two paths towards basal extrusion. And then this led basically to the final figure where we then said, oh, maybe instead of this linear textbook sequence of EMT, there could be this interplay, that there are many multiple paths which all together lead to basal extrusion. And part of this is also when your neighbors are extruding, they might carry you with, you can maybe follow your neighbors. Even if you are not very efficient at extruding basally, all your neighbors are going there, you have chances of also ending up there.
Do you have any experiments to confirm or disprove your data suggestion?
So this is so for the protrusion, the experiment is a bit more complicated. So what Eric did is he did upregulation of alpha integrins. So alpha 4 and alpha 5 integrins. So what are these? Integrins are cell adhesion molecules between cells and the basal matrix. So if a cell is migrating through the basal matrix, it needs these integrins. And now you can make it so high that it's not effective anymore. And then you could see if in this setting cells are successful. So do cells need protrusions in order to leave the tissue? And by his upregulation experiment, he could show that they need protrusion, and if protrusion is not there, they fall off on the apical side. So he had an experiment which shows this falling off in the apical side, like from the bad simulation case. But a biologist would now say that alpha integrin also affects other factors, like the polarity. So there's no 100% proof. There's just some evidence.
Cool.
So this is a hypothesis. We cannot prove it. Yeah.
Oh, already amazing.
Yeah, a lot is like Eric is good at selling, like putting it into biology terms, I think. Yeah. Yeah. So we use the same model for gastrulation in the mouse and also for rosetta formation in flies. And for this is not published yet, but accepted last week. So I was very happy. Yeah, and I think that's the nice numerical method by NVIDIA, and then we use that to model EMT. And this work was a collaboration with Sarah Marino, my PhD supervisor, Eric Thevenau, the biologist, and the moment I'm working with Vuk Milicic on extending this to different models of cell migration. Yeah, thank you very much.
Thank you, Steffen. Wow, for this very interesting talk. So in his talk, we learn math, we learn numeric, we learn modeling, we learn application. You already give 4 talks at the same time, okay? Amazing. Yes, thank you very much. So yes, any question, comments, remarks from the audience? If yes, then just unmute your microphone and ask. Maybe let me start one question. You say you spent 1.5 years to find a correct framework to study these long-source dynamical systems, right?
Mm.
And I learned that this theory was already established maybe 1 or 2 decades ago. So what happened? What have you tried and failed? And in the end, you found a correct theory. What is the story?
Yeah. So I think I was too much looking at Lagrange multipliers.
Lagrange multiplier, yeah.
Yes. And I read a lot of engineering books.
Yes.
And I think that's like I spent too much time on the wrong direction. And one thing is also that I feel like the conditions which are required for the application are not really the conditions the people, the experts in the field are interested in. Like the experts in the field were interested in time dependency of your feasible set. So there were many publications which looked inapplicable to me, but actually, like if I would have followed back to those publications, I would have found the right. And the computer science community is very disconnected with the math community here. Yeah.
So one day somebody told you the correct framework, or you just coincidentally found correct reference, or so what's the bifurcation point? One day you suddenly found a correct framework, or
yeah, I think it was one publication. Like I found there was the work by Juliet Venel, and this paper opened the door.
I see.
Yeah.
I asked you this question because I had a similar situation when I was when I studied PhD. Okay, I spent 2 years using a wrong approach to study my PhD. And one day, my advisor recommended me a paper by Paul Rabinovic, an expert in bifurcation theory. And then I spent only 1 month to finish my PhD. 1 month. And I feel that my advisor already know I was working on the wrong path. He already know, but he didn't tell me until 2 years later. Because in Germany, you have to finish your PhD normally in 3 years. I think, okay, time's up. Okay, he told me, please take a look at Rabinovic's paper. 1 month. But yeah. Thank you. Interesting. Yeah. So question, comments? Yeah, and again, okay, let me ask. As a mathematician, I am very curious about. So because you skip this part, but maybe now you can spend some time on this. Why can you overcome this convergence issue for first order dynamic, and what are the main idea? No. You have already explained the main idea. Sorry, this projection composition, but can you briefly explain the proof about the convergence, your theorem?
Yeah, so this is numerical analysis.
So you have a theorem, right? And you skip
Yeah.
the proof.
Yeah, I can show you.
Yeah. Of course, I can read your paper, but since you are
Yeah.
here,
Yeah. So
yeah.
the theorem is long, but all we need to know is, okay, we have uniform Bragg regular, and then the first part is, if we look at this image here, the numerical method will work like this. We start at xk, then you do one Euler step, then you get this Q0, and then we do the projection onto the smaller set.
Yes.
So you can see that PS of Q0 is where we would like to be, and Q3 is where we end up with our numerical method.
Yes.
So we need to find an error bound for this distance.
Yes.
That's the part, for convergence, the part.
Yeah.
And then we want that our limit is a solution as well. And for this, we need the following property. So if I look at this xk plus 1, this is the same as xk plus a Euler step. And then all these arrows from Q0 to Q1, from Q1 to Q2, from Q2 to Q3. And the nice thing is each of these individual ones is a normal vector to the S1 set and to the S2 set and to the S3 set. So we have a sum of normal vectors. And that means you need to know, oh, does a sum of normal vectors from the individual set converge to the normal cone of the union set, of the intersection set? So, and this, there's a theory for. There's a scalarly upper semi-continuity, some convergence measure. And then this part I will basically skip. So this scalarly upper semi-continuity property you can show for position-based dynamics. It's very easy in a way. For this property, somehow, like, it's a lot of notation, but it's like in a PD when you do test function. So you have a test direction V in which you test, and then you need to show if your differential inclusion is satisfied in the test direction V. And if that's the case, then you're happy. And it is the case for position-based dynamics in the limit. And this is the weak limit, which is the second part for the error, the projection error. So this is, you can imagine a visual. Like here I have this plot, and then imagine the first black dot is my starting point of the projection, and the true projection is the red point. And the worst thing which can happen is that I go in the wrong direction, away from my real projection. So let's say to S1, and from S1 I go to S2, and from S2 I go to S3, and so on and so on. And I'm trapped going into the wrong direction. So it turns out that this image here is the worst case. Only if I'm very close to the next constraint, then I can move far away from my true thing. And metric calmness is a bound for this distance to the closest constraint compared to the distance to the true. Satisfied for contact dynamics that we can prove. So we have this condition for our application.
Okay.
And then we have hypermonotonicity, and these two together, you just play around a little bit, and then you can say iterative projection minus real projection is less or equal than L, and then compared to my distance to the set. So Q is this first black dot, P S of Q is the red dot, and this iterated projection is a black dot here on the left. So the orange line and the red line, I have an inequality between the two. This means if I'm close enough to the set, then the projection is not too bad. Yeah, and this L, I think, L is less than 1. I forgot to write it down here, but L is less than 1. You can prove that. And that's then what you need.
Yeah. So So let me make sure. So you have a Prox regular set, right? And this set gives you hypomonotonicity.
Yeah.
Right?
Yeah. Yes,
But,
of the normal cone.
But does this set give you subregularity, this metric corners?
Mm.
Or you have to assume, is this a
Yeah,
yes? Sorry, you are frozen. Yeah.
The Prox regular sets might not have
Extra
this
assumption.
property. Yeah, extra assumption.
Okay.
Yeah.
Ah, wow. Wow, delicate. I see. I see. Cool. But does your proof work for second order dynamic or arbitrary order dynamic? No.
No,
Why?
it does not.
Why is the reason?
Second order dynamics need a different theory of measure differential inclusions, and there is a jump in the velocity. If two particles collide, the velocity is left-right, and then at one instant it swaps to right-left. So it's continuous velocities, and I think the one needs to find a different numerical method to resolve that correctly.
So your method and proof are really specific for first order.
Yeah. Yes. I would love to do it for second order if someone wants to work on that, but yeah, I think it's very hard. Yeah.
You know, for mathematicians like smooth guys like me, you know, every ODE can be made as a first order dynamic. So, you know, they are not really different. But for you, that's really different. I see. Okay.
Yeah. I think here you cannot do it. There is also, you can approximate non-smooth dynamics as a limit of smooth dynamics.
Yes.
So there's also this methodology. But if you do that for second order dynamics, then I think you get very bad convergence properties.
Yeah.
And actually, there's a big paradox for rigid bodies. If you have rigid bodies and Coulomb friction, second order dynamics, there's no uniqueness of solutions.
I see.
So classical physics, we always think every classical physics model is well posed, but this is like a hard inequality is a human imagination. In reality, there's but the real differential inclusion system is actually not well formed in that case without tricks. Yeah. So very complicated.
Okay. So, sorry, other questions, comments? Yes. Yeah. Our audience are too polite. No,
no worries. It's also online, and I understand.
I just suddenly have one, how to say this? One idea, one phenomena. Maybe you can give me some advice, like because in Taiwan or maybe also in Japan, there are many people are interested in synchronization or collective phenomena, like synchronization phenomena, like butterflies, their flashlight, initially the frequencies are different, but then they converge. Okay, in time, and that's a famous Coulomb model. Like synchronization. People want to study synchronization, but they always ignore contact effect. For example,
which effect? Contact effect. Yeah.
For example, butterfly never contact, right? And this oscillator, they cannot collide. They cannot contact. And I am not sure whether, including this contact effect in this synchronization phenomena could be an interesting research direction.
Yeah, I think there's the VSEC model, which to some degree integrates like synchronization and location.
You mean Cooker-Smell, something like that, or?
Yeah, something in that, yeah.
Yes. But Cooker-Smell, yeah, sure, true. But Cooker-Smell, in my opinion, it's in some sense too complicated. So my point is, even the simplest phenomenological model, the Coulomb model one, I don't think people are already understand it completely. But you are right. Maybe these broken models and Cooker-Smell, they already involve this. Not true.
Yeah. So I like there's one. I will just, it's easier if I just show you. I work on synchronization also.
Oh, is that really cool?
And maybe this is fun. Like this is a video of some snails.
Yes.
You hear tiny fish.
Yes.
And whenever they meet, they wiggle around for a little bit and then go different direction.
Yes.
So this I took a video in Nara. You can see it's here. This goes there, blub, 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 and then goes away. This blub, blub, blub goes away.
Oh, yes, interesting. Yeah.
So and cells are doing this.
Please, yes.
Cells are doing the same. Like cells also, they meet. Then due to contact inhibition of locomotion, time passes. And then they may go opposite direction, same direction, like, yeah, complicated. So the time delay. What happens if your synchronization, there's a penalty for time delay at contact? Yeah. But in this model, if you have zero, like collision is instantaneous, then it's really easy to make synchronization. Just two particles, if they collide and they go opposite direction, instantaneous, then you put the particles in a box, they all go left, right, perfect synchronization. Like published by Woods in 2014. But you add 5-minute delay in the contact and then go opposite way, and they don't synchronize anymore.
Cool. So this is like a desynchronization by delay, induced by delay.
Exactly. Yeah.
Do you have a model? Do you have any model about this?
So the model is very complicated. So you will not like it. I can show you, I can send you the PDF, but like we use this plea-to-taxis, force-dependent synchronization. But it's too complicated for nice mathematics.
I see. So in Coulomb model, people already study the effect of the time delay.
Oh.
And okay,
I didn't know that.
Yeah, small time delay does not destroy the synchronization structure because mathematically there's a theorem, there's a slogan called small delay don't matter. We can rigorously prove small delay cannot destroy, the dynamic without delay. But how about large delay? Usually large time delay can induce oscillations. You can have a whole bifurcation of a periodic solution and many kind of. People can even find chaos. Yeah. Yeah. But today I am more interested in the elementary, the simplest Coulomb model, but now consider contact effect. And maybe, the standard Coulomb model, the phase, they consider phase, so which is in S1. Maybe like the Cooker-Smell, yeah, if you consider manifold, what happened? Yes, yeah, but this may be too complicated.
Yeah, but you're right, one could make Kuramoto.
Yeah.
That I don't know if people did that. That would be not so complicated to simulate, at least.
Yeah,
yeah.
I believe so. I just have no experience in this contact dynamic, but I think your research, especially your numerics, your algorithm, would be very significant if people one day they are interested in this contact contact effect. Yeah, amazing, really.
Thanks a
Yeah.
lot for the cool questions.
Yeah, thank you.
Yeah.
Okay, so any question, comments? Yeah, if this is not the case, I think we can finish the session, the webinar talk now. Okay, see you, the audience. Bye-bye.